All right. Thank you all so much for joining us for the Socorro and GCUS hosted webinar. I'm so sorry for the technical difficulties, but we're going to go ahead and get started, and I want to thank you all so much for sharing your lunch hour with us. Socorro Southeast Coastal Ocean Observing Regional Association in GCUS, the Gulf of Mexico Coastal Ocean Observing System, are two of the 11 regional associations that make up the NOAA U.S. Integrated Ocean Observing System, also known as USIUS. IUS is essentially the weather service for the coastal oceans and Great Lakes, providing the ability to see what is happening both above and below the surface and making that information readily available. Socorro and GCUS work together to observe, understand, and increase awareness of our coastal ocean, especially in the Gulf of Mexico. My name is Abby Wakely, Socorro's Communication Director, and I will be facilitating and moderating this webinar. All participants will be in listen-only mode. You are encouraged to type questions for the presenter or technical questions for me in the chat box. I will respond to them directly or post the questions to our presenter after his presentation. We are recording this webinar today and will be posting the recording along with the PDF of the presentation on the Socorro website. Today, we are so excited to welcome Dr. Nick Shay from the University of Miami. His webinar today, Resolving the Loop Current Complex, Implications for Hurricane Intensity Forecasting, will highlight how measurements such as ocean current, temperature, and salinity fields are used to evaluate coupled forecast models and improve hurricane forecasts. Dr. Nick Shay holds a PhD and a Master's of Science in Physical Oceanography from the Naval Postgraduate School and a Bachelor's of Science in Physical Oceanography from Florida Institute of Technology. He is currently a professor in the Department of Ocean Sciences at the University of Miami's Rosenstiel School of Marine and Atmospheric Science, and he directs the Upper Ocean Dynamics Laboratory. He has published over 115 peer-reviewed publications in top-tier journals and books and has chaired or served on 40 student committees. The overarching goal of his research is to conduct scientific and technological investigations that require both basic and applied research activities that have societal relevance at its core. Dr. Nick Shay, thank you so much for joining us. I'm going to go ahead and promote you to presenter.
My name is Nick Shay from the Rosenstiel School, and we've been looking at this complex phenomena for a number of years, dating back to 2000. Okay, so a number of agencies have been supporting us over the past 2 decades or so to try to understand not only just the loop current, but its potential for increasing intensity of Gulf storms, and in particular major Gulf storms that have entered the Gulf and have a well-developed circulation and begin to sense the loop current. And as you will see as we go through the talk, we're going to emphasize the importance of the observations. Observations are really crucial to try to understand the physical processes and to ensure that we have data to evaluate both oceanic and coupled models for intensity change. So the motivation is pretty clear. We've seen storms like Katrina and Rita, as well as several other storms. Once they encounter the Gulf of Mexico loop current, they often explode from to severe status, that meaning Category 3 or above. And we've had a number of flights courtesy of NOAA, HRD, that's the Hurricane Research Division, as well as working with the Aircraft Operations Center in deploying sensors from aircraft before, during, and after. I give a list here on this slide. We looked at Isidore and Lily, Katrina and Rita, and Gustav and Ike. More recently, Isaac, and then last summer, Nate. Nate actually ran over a couple of our profiling floats that we had deployed in support of our GOMRI project in the Gulf of Mexico, trying to measure the physics as well as the biochemistry. So 3D observations are critical. That's pretty obvious, and you need those observations, as I alluded to earlier, to resolve physical processes as well as understand what the models are doing in terms of the coupled response between the ocean and atmosphere during the strong wind condition. So let's just go back to the Deepwater Horizon year, and starting in April. And what I'm showing is just a movie of, we know how complex that loop current was during that period of time, eventually separating what was known as Eddy Franklin. Eddy Franklin was a fairly large eddy that was shed by the loop current, and you can see how the loop current then retracts back towards the Yucatan Straits and towards the Florida Straits. So this is a complex region, and we need to understand it better, and that's where the observations come into play. And I just want to say that one of the motivating factors for us during the Deepwater Horizon was we needed to map out the loop current structure as part of work with ongoing work with NOAA and at the time Minerals Management Service. So in the next slide, we basically had 9 or 10 flights starting in May. It's shown in the wind speed time series at the top of the panel. Here, wind speeds were relatively benign compared to, say, hurricane force, but you get a feel for not only just the complexities of the upper ocean, the strong currents and the current field itself with its thermal structure, but you also get a pretty good feel for how dynamic the boundary, the atmospheric boundary layer is above the loop current, even under relatively benign conditions. And we show that by looking at what is known as equivalent potential temperature. And equivalent potential temperature can change significantly going between what's happening over warm water versus what's happening over cold water, and that's depicted in the insert, looking at the cold core eddy, where the theta E was less in the boundary layer than what it was over the loop current during this period of time. So here's the next slide, basically shows a hurricane, and we know a number of things occur underneath the hurricane, and what lies beneath in the ocean has an impact on what the atmosphere feels during hurricane passage. In particular, we get upwelling underneath the track, shown by the red arrow right in the center of the track. To the right of the storm, vertical shear gets developed through strong wind-driven flows, and it is that vertical shear that we try to resolve to try to understand how much cooling is going to happen underneath the storm, how much upwelling is going to occur. These processes are really first-order processes in understanding the oceanic response to the passage of a hurricane. Now, we've given approximate amounts of ocean mixed layer cooling, and the ocean mixed layer turns out that in a place like the loop current is fairly deep. That just means that there's more upper ocean heat available for a storm, and the deeper that layer, the more sustained the heat fluxes are. When I say heat fluxes, I mean both the sensible and latent heat flux. In addition, so the upwelling is basically a response to the net integrated transport induced by the wind stress field, or the curl of the wind stress field. And that allows the upwelling to occur underneath the track, bringing cooler water from the thermocline up towards the basin mix layer. So it's a complex circulation that's induced by strong winds, even in the absence of a loop current. And what we've tried to understand as part of the research is how much mixing might be going on, how much upwelling might be going on, as well as what are those heat fluxes that are needed to try to understand what's going on in a coupled model versus what's happening under quiescent conditions. So it's pretty important in terms of sustaining a strong hurricane. And the other part of the puzzle here, of course, is each time these major storms go over places like, warm core eddies or warm core rings, or the loop current, they often intensify, as I alluded to earlier. And usually what you see are these eye wall replacement cycles. So briefly, what an eye wall replacement cycle is you get the formation of a secondary eye wall, and as that secondary eye wall grows, it comes closer to the center of the circulation, and it replaces that initial eye wall. Most very strong hurricanes go through these eye wall replacement cycles, and for example, Irma last year went through 6 or 7 of them right before she made landfall in Florida. So the next slide sort of summarizes what we just said. On one side, you have the weak current shear and the cooling. So when you have very strong ocean currents, and we'll see this during the talk from the data sets, strong background flows like the loop current often preclude really the development of strong vertical shear. That basically means there's just more heat for the storm, and it's the vertical shear at the base of the mix layer and in the upper part of the thermocline that drives the cooling. It just so happens, like in regions like the loop current and the warm core eddies, that mix layer is very, very deep. So when I say very deep, somewhere in the vicinity of 50 to 100 meters deep, and that precludes a lot of sea surface temperature cooling that we often see from satellites in the wake of storms. Now on the right side, you see it's markedly different when you're interacting with a cold core eddy. A cold core eddy is basically cold water is much closer to the surface, the mix layer is much thinner, and under those circumstances, shear in the ocean really gets excited, and that shear in turn causes significant sea surface temperature cooling. So that sea surface temperature cooling is our first inclination that when these storms begin to encounter both warm and cold features, like in the Gulf of Mexico, it's an indication of how much mixing and sea surface temperature processes are being affected by essentially the depth of the thermocline. So why is the Gulf? So here's an example of why the Gulf is so important. During the passage of Katrina and Rita in '05, basically what we saw was over 35% of the rigs were destroyed or damaged by strong winds, and obviously the wave field being generated by it. In the lower panel, what we've done is we've gone through the literature, and we've come up with an envelope of typical loop current, warm core ring separation, and it's very slow movement towards the west-southwest at a few kilometers per day, which is sometimes even faster than Miami traffic. So if we go back and look at the tracks, and I'm going to focus the attention on number 2. Number 2 is Hurricane Camille, and so this is the misconception that a lot of folks believe, that the storm has to go a long way, like of Cape Verde origin, to make its way all the way across the Atlantic and get into the Gulf to be intense. Well, Hurricane Camille started right off the tip of Cuba and essentially went north-northwest and really had a significant impact on Gulfport and Biloxi back in 1969. 200-mile-per-hour winds at landfall, and one of the things that we do believe that part of Hurricane Camille went over the loop current itself, which can account for a large fraction of the rapid intensity change that we've seen in Hurricane Camille. And we've seen other storms do the same thing. As I alluded to, Hurricane Lily, Hurricane Katrina, Hurricane Rita, and the list goes on. So it's more than just circumstantial of why we need to resolve the loop current and understand its interactions with the overlying atmosphere. So what we've done here in this slide, we've shown what on the left side, it's one of those counterclockwise rotating cyclones in the ocean. What you see is a typical mixed layer depth of 20 to 30 meters, and the depth of the 26-degree water is about the same, in roughly the same place, but the depth of the 20-degree water is typically around 80 meters. And what that equates to in ocean heat content, that's what the equation is in the center of the slide, all relative to 26-degree water. Shows about 6 or 8 kilojoules per square centimeter, which isn't a lot of heat. By contrast, if you look at the anticyclone or the clockwise rotating warm eddy, typical mixed layer depths are down around 68 to 70 meters. Depth of the 26-degree water is around 120 meters, and the depth of the 20 is around 250 meters. So what does that mean? It just means that you have heat content now that's over 100 kilojoules per square centimeter. And keep in mind that some early work by Dale Leeper and his colleagues in the Gulf of Mexico, they suggested that the magic number was somewhere between 17 to 20 kilojoules per square centimeter to maintain a hurricane. And of course, with heat content over 100 kilojoules per square centimeter, there's more than enough heat available to the overlying atmosphere to help with the intensity change. Okay, so we're going to go back to O2, where we did a series of experiments from the NOAA P3s, and we looked at what the ocean was doing underneath the storm. For example, in panels A and B, these were our pre-storm grids. We often go out and do pre-storm grids because we want to really try to understand what's there before a storm comes through, particularly in this area, the Northwest Caribbean, going through the loop current. These areas are really particularly important because they have a lot of heat and a heat content. Of course, when we lay down those pre-storm grids, you're always susceptible to Mother Nature's whims, and you can see in those top 2 panels with the track of Isidore, instead of Isidore going directly over our grids, she actually went between the 2 grids. So notwithstanding, we still went out with dual aircraft and did a survey, an in-storm survey, dropping a bunch of expendables from the aircraft. And these expendables also include GPS sondes. A GPS sonde measures temperatures, winds, and pressures, as well as moisture. So it gives us a pretty good clue to estimate the heat and moisture fluxes going from the ocean to the atmosphere. Of course, unknown to us at the time when we laid out the pre-storm grids in panel A and panel B, what happened? Well, Hurricane Lily followed a week to 10 days later. You see in the Gulf of Mexico, often you see tandem storms. So Isidore and Lily was another one of those tandem storms where essentially Lily was following the wake of the hurricane itself, of Hurricane Lily. And what we're seeing is that we were able to go out before the storm, during the storm, and after the storm to map out the ocean structure, try to understand the ocean's influence on Hurricane Lily. Lily, of course, strengthened to Category 4 storm status. Very strong storm in the central Gulf of Mexico. And of course, it worried the folks in Louisiana because Category 4 storm in the center of the Gulf meant that Louisiana could be significantly affected by a strong hurricane, and there lies the problem. It's not just rapid intensity increases, but also rapid intensity decreases pose a major challenge in the forecast models, and that's precisely what happened. Hurricane Lily decreased in intensity to a Category 1, and that's fortunate for the folks of Louisiana. But the point was that we went out and laid out these grids in the loop current, and then just towards the north in the loop current, in the loop current, as well as what is known as the Gulf Common Water. The fluxes are essentially what we expected them to be. For Lily and Isidore, they were on the order of a kilowatt per square meter, with Isidore a little less, with Lily a little more, because Lily was a more intense storm. And we derived these quantities using what is known as a step frequency microwave radiometer that's on the aircraft. They essentially measures wind speeds with respect to the surface, and then from which, when you combine the step frequency microwave radiometer data with those GPS sondes, you can begin to estimate the fluxes fairly well using the bulk formula. So what happens across the Yucatan Straits? Well, before the storm is the upper level panel prior to Isidore, and then after Isidore, what we actually saw was this upwelling in the lower panel right across the shelf. And what did we see? On the shelf, the shelf of the Yucatan, we see 4.5 to 5 degree cooling. That was primarily due to strong upwelling signal over the shelf. But in the center of the straits, the Yucatan Straits, we saw less than a degree cooling. And that's sort of the number that we see in the loop current and the warm core eddies during hurricane passage, about a degree cooling. Okay, so what we're looking at now in the upper panel was that section going from the straits all the way up north of the loop current. So BB prime actually means that this is a section. So you can see essentially on the left side is the Gulf Common water, and you see really significant current and current shears being generated. Well, that lended to cooling of about 3 to 4 degrees C just north of the loop current. However, in the loop current, which is typically on the right side of this B prime B section, you see very strong background currents. Those strong background currents associated with the loop current coming through the straits basically precluded active development of strong vertical shear, which basically meant that the ocean wasn't going to significantly cool. And in fact, we see that in the data set. So I wanted just to compare and contrast that with the vertical structure of the currents. Again, left side around B prime, strong near inertial motions. In other words, these motions are close to the local inertial period. Whereas on the right side, close to B, not much is happening in terms of the near inertial waves being generated by the strong winds. In the lower panel, I brought that in because I wanted to compare and contrast that to what we saw in the cold core eddy and the warm core eddy that both Katrina and Rita passed over. These are from moorings that were, these data are from moorings that BOEM actually provided to us to try to understand the current response during Katrina and Rita. So this is a nice segue now into what happened during Hurricanes Katrina and Rita. In the cold core eddy, for example, you see very energetic near inertial currents in response, and there's a lot of vertical shear. More cooling, lots of shear, more cooling, not much shear, not much cooling. And you see that basically in the warm core eddy to the right. You see near inertial response, but the shear is not there. And the shear is what causes the mixing and the cooling. So here's really the poster child for what happened during Hurricane Katrina. As many of you know, Hurricane Katrina made landfall in Dade County. It essentially cut Dade County in half as a Category 1, Category 2 storm, reemerged over the West Florida shelf, and then begun a turn towards the north. And in the area of the loop current and the warm core ring, you can see in the top panels how that wind field really got wound up as the storm encountered this strong current field with heat content in excess of 100 kilojoules per square centimeter in this particular case. And as in Rita, both of those storms had fairly favorable atmospheric conditions. Not much shear in the atmosphere, good circulation, good inner core physics, and very warm water. And so the warm core ring is to the left. We had the loop current, and of course, the loop current flows out of the Florida Straits as the Florida current. So we have to be aware of this current system, particularly for those of us who live in Florida around this very warm water. In the lower panel, what you see, that's a sea surface temperature image. So a sea surface temperature image, while important, didn't really show where the structure of these sources of high heat were located. So it's important. And one of the things that we've done over the past 20 years, we've begun to do these heat content maps from space, getting altimetry data each day and redoing the calculations, so forecasters can at least have a good idea where the sources and sinks of heat are located relative to a projected track. So this has become important in the forecasting. So the big question then, is sea surface temperature really enough? And I say no, it's not. And in 2005, we had the trifecta. We had Katrina and Rita. Rita actually followed Katrina's path pretty closely. There was some divergence at the end as it was going towards the coast. And we also had Wilma, which was a very intense storm in the Yucatan Straits and made landfall in the Keys, 882 millibars. So I call that the trifecta from 2005. And so here's the depiction of Rita. So Rita was following essentially a similar track to Katrina. So the conventional wisdom would be that, well, the storm has moved over this region, so it's probably really mixed, so there's probably not much heat. Well, in fact, you can still see that the loop current, while it cooled by about 20 to 30 kilojoules per square centimeter, it still had more than 100. So that meant that, again, you still have deeper, warmer water that could potentially fuel the storm. And in this case, Rita also went through an eye wall replacement cycle and reached Category 5 status, again, close to the center of the Gulf, which, of course, for forecasters makes it a little hairy when storms are barreling towards the north and towards the the northern tier of the Gulf of Mexico. Again, there's the warm core ring. Now the cold core ring is obvious, and then the loop current, and we see what that structure is. So what we did is we differenced the SST maps. So this is from courtesy of Shell Gentman, her TMI product, and you can see where the cooling really actually occurred typically about 2 to 2.5 degrees C towards the right of the track of Katrina, and similarly the maximum cooling for Rita occurred to the right of the track, but still there was a lot of heat available for both of these storms as they moved towards the north in the Gulf of Mexico. Now, I would like to say that we had this planned. One of the things that we did is we did a post-Katrina flight. We couldn't get on the Katrina flights, but we did a post-Katrina flight. One of the big questions was, well, how much heat did the warm core ring or the loop current lose during that period of time? So the left panel represents pre-Katrina or post-Katrina, which, unknown to us at the time, Rita came through about 11 days later, turned it out to be post-Rita. So we went out and done surveys, and that's in the upper right side where we've dropped drifters. We dropped expendable probes. We dropped GPS sondes in a star pattern to try to understand what was going on in the warm core eddy field, as well as the cold core feature. And in the lower panel, you actually see a cross-section going directly across the eddy field from our measurements. And you see the loop current. The cold core ring was a little north of the feature, as well as one a little bit south and west of the feature. But what actually transpired when Rita came through is you can see that that cold core ring after Rita, the post-Rita, clearly came between the warm core ring and the loop current as a result of the strong wind field. So the wind fields are particularly important here because the winds are driving a lot of the upwelling and the mixing, of course. And you can see that in the lower panel, that would be panel D, and you can see how that cold core ring got wedged between the loop current and the warm core ring, and the heat content went to 0. That basically means 26-degree water or less was surfacing between these two features. So the wind stress curl of Rita did have some sort of an impact on the shedding process of this warm core ring. So winds are particularly important in this, trying to understand this. So we took some of the data that was collected, some of the mooring data that was provided by BOEM, and we looked at what the ADCP currents were doing, and you can see from the ADCP measurements how current structure was changing. This is to the right of the storm, and you can see pretty strong near inertial motions, and you see basically an upward propagating phase, and the upward propagating phase basically means a downward propagation of energy, and that's been shown in several other studies. So the moorings were equipped with temperature salinity sensors as well as the ADCP. So in the cold core eddy, we saw stronger mixing. That's as depicted in the temperature and salinity diagrams. Okay, so pre-storm is red, during the storm is green, and post-storm is blue. And you can see how much cooling and changes in the salinity occurred as a result of Katrina and that cold core eddy. By contrast, the warm core eddy that was affected by Rita, again, it's the same depiction. Pre-storm is red, during storm is green, and post-storm is blue, and you can see significantly reduced mixing, and that's because warm core eddies or warm core rings have very deep warm mix layers. So not much vertical shear on the right side in the warm core ring or eddy, and a whole lot of shear in the cold core eddy, which is consistent with what we've been seeing in other cases. So here's the differentiated cooling in the loop current system that we published back in '09. In the loop current, we typically see a delta T of about 1 degree C, whereas in the shedding front, we see about 4.5 degrees C changes. That could be a cold core eddy coming through, or that could be significant mixing going on because and upwelling, as well as in the warm core eddy, we typically see a temperature change of about 0.5 degree to 1 degree, which essentially means that the warm water is pretty deep, and there's more of a sustained air-sea heat flux feeding the storm. So that was '05, and many of you probably remember '08, where we had two fairly strong storms again entering the Gulf. It's interesting that it's another tandem separated by a week to 10 days. And of course, Gustav was a Cat 3 storm getting into the Gulf of Mexico and making landfall somewhere in Louisiana. And we dropped a whole bunch of AXPTs, GPS sondes, drifters, and floats to try to understand the response, particularly north and west of the loop current. We have a pretty good feel of what the response was in the loop current itself. And then 10 days later, roughly, with Ike. Ike was one of those storms that, while it was only a Category 2 storm, it had horizontal structure as if it were like a Category 4. So it was a very broad, strong wind field that had a significant impact on the storm surge as well as the coastline. And you see that here in terms of the sea surface temperature cooling. On the right side of the track, again, this is over the West Florida shelf, and it's not in the core of the loop current, in the upper panel. And then during the passage of Ike, you clearly see very strong cooling to the northwest of the loop current itself. So again, these, excuse me, these contrasting areas of how heat is being changed by the strong winds as well as the mixing and upwelling away from the loop current is pretty obvious. By contrast, in the loop current, you don't see nearly the levels of cooling because shear is not being generated by the winds. In 2012, we also went out during Hurricane Isaac. Isaac was a slow mover moving through the Gulf of Mexico. It's the same type of deal where we did pre, during, and post, and you can see that in the summary of what we actually performed during that period of time. And you can see that there was some cooling going on, particularly underneath the track. That was largely upwelling because the storm was moving quite slowly. And storm translation speed becomes critical in the upwelling because it goes, the amount of upwelling actually scales by 1 over the translation speed. So the slower the storm, the more upwelling, the faster the storm, the less upwelling, but the more mixing that actually occurs. And the different colors in the plan in the lower left are the different types of sensors, the XBTs and AXCTDs, which are just CTDs from airplanes, and the XCP is a current and temperature profiler. So what we did is we looked at the left side of the storm had a warm eddy, the right side had a cold eddy, and of course the storm went between the two. So you can see on the left side, currents were being generated, strong currents were associated with background warm core eddy, whereas by contrast, on the right side of the storm, where we see mixing processes going on, you can look at the current structure. It's in that upper right-hand panel. You see the winds, and then underneath you see the currents, and you can see tremendous current shear being generated by the wind field. So again, this gets back to what happens underneath or during deep water horizon. We saw high theta E values in the loop current and warm eddy, whereas these theta E values are much lower over cold features. So this is one of the consistent findings that we're seeing in the atmospheric boundary layer. So these are important considerations with respect to the storm. And this is just another summary showing upwelling and mixing in the upper reaches of the TS diagram, whereas in the lower reaches, it's just more or less upwelling going on. One of the things that we actually learned from this slowly moving storm is we went back and looked at the work by Stern back in 1965, and there's really two components to the vertical velocity. We're all familiar with the upwelling velocity being driven by the curl of the wind stress. That's the linear term, but there's also a second term where you have to take into account the background geostrophic flows, which can actually enhance the upwelling velocity even more as it's projected onto the wind stress, or the actual wind stress. So that's the lower right-hand panel, and you can see the broad wind field that was associated with, and that's the black contour, the heavy black contour that's associated with the wind stress field associated with Isaac. Again, this was a slow-moving storm up over the northern reaches of the Gulf of Mexico. So this gives you another viewpoint. Not much cooling going on in the warm eddy, lots of cooling going on in the cold eddy, okay? So when I say, and then in fact, we saw some sort of a warming in the warm core eddy as a result of horizontal advection tendencies. So understanding how these processes are interacting during the passage of storms is critical if you want to get the forecast right. And here's just another depiction. On the left side, we see downwelling. On the right side, we see upwelling. And again, it's dashed lines for pre. In storm is solid black, and then post-storm are represented by red. And you can see this contrasting upwelling and downwelling between these warm and cold ocean features that already existed prior to the passage of Isaac. Okay, so last year we were fortunate in that we went out and deployed a whole bunch of sensors out in front of Hurricane Nate, because Hurricane Nate was predicted to become an intense storm in the Gulf of Mexico. However, Hurricane Nate all of a sudden went from a 10-mile-per-hour translation speed all the way up to about 22 to 25 miles per hour. So it was a really fast mover. But the good news was, and it's the green, the light green in the lower panel, we had a bunch of floats out there that were part of our Gomery project. And in fact, I'll show you in a minute the current and the temperature and the salinity changes induced by Nate. So it was fortuitous that, the floats were, a couple of floats were still there. And then we went out on the aircraft to make detailed measurements of that warm eddy that had just separated from the loop current to try to understand what was going on in there and whether or not it was going to have a big impact on Nate's intensity. With Nate moving so quickly at 20+ miles per hour, it had little time to pick up the heat and moisture from the loop current itself, and I think it only reached Category 1 prior to landfall, which was fortunate enough for the folks living in the northern Gulf. And of course, the upper level panel shows, again, SST. The SST doesn't give you the full clue of what lies beneath. So what lies beneath becomes really important. So this slide, it's a little busy. So over to the left is what one of the floats looks like. The center panel here shows temperature and salinity changes before, during, and after. And in the upper right-hand panel, you see where the float was located. The float was located just on the perimeter of the warm core eddy, or warm core ring. And the velocity response is in the lower right-hand panel that shows strong currents being generated by the wind field. And to look at that in more detail, what we did is we just looked at a bunch of stills, and you can see the complexity of the current field even under a hurricane Category 1 storm. So that becomes important. And again, when you start thinking about the basic physics involved, again, upward phase propagation and downward propagation of energy, that's basically what we're seeing again in this data set. So again, the current is really important in this problem. The current actually drives a lot of the SST changes and the SST cooling, the mixing, and the upwelling and downwelling. Now, we did a little bit of work on Ivan, and I don't want to belabor this point too much, but we're fortunate enough to work with NRL and Bill Teague, and we looked at some of the ADCP moorings located in the right panel. And working with George Hallowell, we went through and we looked at not just the current, but the sheer magnitude of these moorings that were influenced by Hurricane Ivan. And you can see the SST response to Ivan, pretty dramatic away from the warm feature that's in the center, basically between the two cold features that was unmasked by the winds in the SST analysis. But in the upper right, what George did as part of the work is he looked at changes in the drag coefficient and the different types of vertical mixing models. The upper panel is observation and its shear magnitude. So we're not just looking at the current, but we're looking at current shear. And basically what he deduced from a series of sensitivity work, the KPP mixing scheme, the one right underneath the observation in the right side shows that it looks like the shear matches up much better than the other two mixing schemes, and the drag coefficient, where we looked at Mark Powell's work, Mark Donlan's work in Large and Pond, and it looks like Mark Donlan's drag coefficient, which drag coefficient is associated with the momentum response and the momentum being injected into the water column by the strong winds. So I'm getting towards the conclusion here. So this is something that just came up for us recently. One of the things that's happening on the West Florida shelf is a very strong outbreak of red tide. So we went back to Hurricane Irma from last year. Hurricane Irma was a slow-moving storm. As I alluded to, slow-moving storms cause a lot of upwelling and a lot of transport in the offshore direction in the surface layer, which means colder water from out beyond the shelf break is being advected towards the coast. And of course, one of the things that this does, these strong winds can mix and upwell things that are either near the bottom or suspended on the bottom and resuspend them back into the water column. And one of the things that we're finding with the 3 to 3.5 degree cooling, this might have been a precursor to the strong red tide outbreak that we're seeing here on the West Florida shelf currently. So in what we've heard from various folks, this occurred, a major outbreak occurred in 1980, and another major outbreak occurred in 2006. So we went back to looking at what kind of hurricanes brushed the West Florida shelf. Indeed, Hurricane Frederick back in 1979, Category 4 storm, very broad wind field, had an impact at the shelf break. We have data to show that. It's not included here, but we did a study during Hurricane Frederick to show deep ocean currents being excited by the passage of Frederick. And more recently, in Dennis and Katrina, went to brush the West Florida shelf and had an impact on that SST response. So they're saying that the major red tide outbreaks have occurred in 80, 06, and now 2018. So this might be a possibility of what's actually happening. So does hurricane passage precondition the shelf, resuspending these critters or organisms into the water column, and as they make their way towards the coast, start interacting with a lot of the fresh water that's coming out of the Caloosahatchee and Okeechobee. So the 800-pound gorilla in the Gulf of Mexico is the loop current. Everybody needs to know where the loop current is. The loop current is important for a number of reasons, but it drives a large fraction of the circulation in the Gulf of Mexico. It's very warm and it's very deep and can affect hurricane intensity. It's pretty clear from the storms that we studied, this feature had a pronounced impact on the hurricane intensity change. Current shear is really important. What lies beneath in the ocean is really critical. We know that current shear and momentum fluxes in the Gulf common water are big, or what we talked about today was cold core eddies. By contrast, in the warm core eddies, you don't see much mixing, nor do you see a lot of upwelling and downwelling going on, simply because these layers are quite warm and deep. And again, the number here that we're looking at previous studies, historical studies, have said that 20 kilojoules per square centimeter is enough. And here we're getting 100 to 120. So there's plenty of heat to provide the heat and moisture from the ocean to the atmosphere. And given the length scales of these, the north-south length scale of the loop current, that's more of a sustained ocean flux, air-sea flux going from the ocean to the atmosphere. So there's negative feedback regimes, the places that cool very quickly, SSTs decrease below 26 degrees, the fluxes begin to turn off. By contrast, there's less negative regimes, but I call it positive regimes, such as the loop current and warm core rings and the eddies. You have to know where they are. They're a major source of heat in the Gulf of Mexico, not only just for hurricanes, but also for winter storms. We saw that back in a case with Emily back in 1993, a winter storm that went up the eastern seaboard that got energized by a warm core eddy. Targeted observations are critical, whether, using expendables deployed from airplanes, drifters, E&M apex floats. We need the current, we need the temperature and salinity. They're not only just needed for satellite comparisons to show how well there's a good level of agreement, but also the coupled model simulations. And the big question marks with the models are, what's the correct vertical mixing parameterization? What's the correct air-sea flux parameterizations, the bulk aerodynamic formulas? What drag coefficient do you use? These are all open questions, still need to be resolved. It's very difficult to get great measurements during high wind conditions. And that's essentially where we are. Thank you.
Great, thanks so much, Nick. Really appreciate the presentation. Seeing that it's 12:58, we'll give it a few minutes for questions. If everyone can type your questions in the chat box or the Q&A box, I will post them to Nick. And Nick, we did get some questions during your presentation, so I'm going to go ahead and start with that. Kent Satterley is asking, how deep do we need to know water temperatures?
I think we need to know water temperatures at least down to the depth of the 20-degree isotherm, because that allows us to understand, that's sort of the point of demarcation between the water masses. So whatever the depth of the 20-degree C isotherm is, that's what we need to know for process-related studies. However, for model initialization, the deeper the temperature and salinity measurements, the better, because what you're trying to do is initialize the ocean with realistic ocean features, which often go several hundred to almost 1,000 meters deep.
Great, thank you, Nick. And he has a follow-up question. Can you comment on the value of using retired offshore platforms for oceanographic monitoring?
Yes, I think using those platforms is a great tool to set up good measurement devices, as long as we can monitor them and make sure that they're calibrated and we're getting quality data from those sites. The key is making sure good calibration and being closely watched.
Great, thanks, Nick. And then we have another question, is how does conceptual model change under ENSO conditions?
How does it change? Well, we know that when we have conditions, say, in the Eastern Pacific, for example, and a strong El Nino, we know that when strong El Ninos occur, we don't necessarily have to worry as much because of the teleconnections to hurricane activity in the Atlantic basin. By contrast, when we have a La Nina condition, we have to be concerned about hurricane conditions over the Caribbean and the Gulf of Mexico.
Great, thanks, Nick. We have time for one more question if somebody wants to type it in. All right, I am not seeing any more questions. Seeing that it's 1:01 p.m., we're going to go ahead and end the webinar. I want to thank GCUS and also Socorro, and also you, Dr. Nick Shay, for giving this presentation.
Thank you, Abby.
And I want to let everybody know that a recording of both the webinar and a PDF of the slides will be available on the Socorro website. And wait, Nick, you have time to take one more question. I do see that's 1:02 p.m.
Sure.
All right, from Scott Curtis, he is asking, is there any relationship to the Gulf Stream in the eastern U.S.?
What happens with the loop current?
Is there any relationship to the Gulf Stream in the eastern U.S.? I believe so.
Yeah. Well, storms moving over the Gulf Stream, just like storms moving over the Kuroshio and these western boundary currents, it's kind of the same scenario. Not a lot of mixing going on because of the strong current structure, and storms often intensify once they start sensing the Gulf Stream.
Great, thanks. Scott, if you want to shoot me an email, if we didn't answer, oh, he said thanks, so we answered his question right. Thanks so much, Nick. Thank you again for joining us, and we'll have a recording of the webinar along with the PDF of the slides on the Socorro website. And
I do like to say thank you to both Socorro and GCUS for hosting this webinar.
Yeah, thank you so much. Thanks, Nick, and thanks for sharing your lunch hour with us. Everyone's sending a lot of kudos and saying thanks.
Thank you.
All right, have a great day. Bye-bye.
Yep, bye.